Hi, good morning. Um, we'll see if anyone else joins on in the next couple of minutes. I figured this would be a little smaller today or this morning. Um, but if there are any specific questions you have, um, feel free to put them in the chat. Um, I don't know if anyone else will join us today. But I have an hour, so if you want to ask any questions, by all means, um, feel free to use this for yourself. Be general, practice exam, anything you would like. Yeah, absolutely. Let me just sign into my iPad so I can share my screen from there. Alrighty, so for question 6, the big thing to note here is the equation that we're using for this question. So for the flashing of fireflies is a result of chemical reaction, and the rate of flashing can be described by the Arrhenius equation. We need to know what that Arrhenius equation is. So this is given to you on your formula sheet. We're comparing a rate constant of 16 at 25 and then at 5.5 at 15. So we're comparing the two rate constants to two different temperatures. So we're going to use the combined Arrhenius equation. So we're going to use the ln K1 over K2, which is equal to EA over R times 1 over T2 minus 1 over T1. So it doesn't really matter what you assign to T1 or T2, as long as you just keep them the same. So, your higher rate constant should go with your higher temperature. And they give that to you at 16 and 25 and 5.5 at 15. So you can label this one as K1 and T1, and then K2 and T2. It doesn't matter like how you arrange K1 or K2 on your formula either. If you put K2 on top, it's the same thing. As long as you make, right, if you put K2 on top, then you want K1 second. Or if you put K2 on top, then you want T2 second in your temperatures, right? So you want them to be sandwiched on opposite sides of your equation. So you can do ln of 16 over 5.5. And we're looking for the activation energy. So we're going to use EA as our X, and then we're going to use our 8.314 as our R value here, because we're looking for something in energy, which is joules. Then we have 1 over T2, we said is 15, that we need to change to Kelvin. So it'll be 288 minus 1 over 298. And then, let me pull up my answer key. So then I would do this so that it's 1.06784 equal to EA over 8.314. This becomes that small number there. I would then divide by 8.314. So you get this. And then you can divide by that small number to get EA by itself. So EA would be 700 or 76,194.75. This is now in joules per mole. And then to get to kilojoules, like you want your answer choice to be in, you're just going to divide by 1,000. So then it becomes 76 kilojoules per mole. And that is that. Does that make sense for how you would do that one? Great. This should be, there should be 4 zeros here. 0.1234. Yeah, 1/4. Yep. So for 11, we have the reaction 2N2O5 goes to 4NO2 and O2. So we want to follow the rate law below at 60 degrees Celsius. And according to the rate law, the reaction is blank order with respect to N2O5, and the initial concentration of N2O5 is halved. The initial rate will be blank. So what we're looking at here is what can we tell from our rate law. So here we know that our order is determined by the exponent that's here. If there's no exponent, that means that it is a 1. So if we have a 1 as our exponent, what is our order for that reactant? Yep, it should be first, so we can get rid of A and D. So 1 equals first order. Right, if you don't see the reactant there, then that means it has an exponent of 0, which is then makes the whole thing 1. So if the reactant is in your elementary step, but it does not appear in your rate law, that means it has a 0th order rate order. So this is going to be first order, and then we can also see that by our units. We know our units are 1 over seconds or 1 over time, and those are indicative of a first order reaction. So then the initial concentration of N2O5 is halved. The initial rate will be halved or doubled as our choices. So if we have, if you have a first order reaction, if our concentration is doubled, what happens to our rate? All right, for concentration is doubled, what happens to our rate for first order? Yep, it's also doubled. So, right, whatever happens to the concentration also happens to the rate. So if our concentration is halved, what is happening to our rate? Also halved, right? So C will be our answer choice here. And if you want to see that written out, you can say that you have, right, rate 1 is equal to the concentration of N2O5 to the first, and right, rate 2 is equal to N2O5 divided by 2 over 1, right? If you divide these, then this becomes, those cancel out, and this is rate 1 over rate 2 is equal to 2. So then to solve for rate 2, you're going to multiply across and then divide. So that's rate 1 divided by 2 is equal to rate 2. So that's showing you that the rate is divided by 2 for your change. Right, so it's showing you that rate 2 is half of the rate 1. Okay, and that would work for any sort of order. You can, right, if it's second order, you can do it that way. If it's zeroth order, you can do it that way as well. Okay, does that make sense for 11? Great. And we said 13. So for 13, we are looking for, right, we have the chemical reaction, and then we have the rate constant for this reaction under experimental conditions is, right? So we need to find the rate constant K. In order to find the rate constant, we have to find the orders of our reactants first. We cannot take the coefficients that are in front of your reactants from the balanced equation. We need to find it out experimentally. So if you're looking at A first, right, we're just going to move left to right. What two experiments are you going to look between to find how the rate changes with respect to the change in A concentration? One and two would work better for C, but we can look at it there. So if we look at 1 and 2, right, we see that from experiment 2 to experiment 3, what do we do to our concentration of C? Yep, so if we go from 1 to 2, it's halving, or if we go from 2 to 1, then it's multiplying by 2, right? So we'll say times 2. But what do we do to our rate? It's the same, right? This is just times 1. So if our rate is not changing, but we have a change in concentration, what does that mean about our order for C? Right? Rate is not changing, but concentration is changing. Does that mean it's dependent on the concentration of C? It shouldn't, right? So if our rate is not changing, but our concentration is changing, that means that no matter what we do to the concentration of C, it's not going to affect our overall rate. So if we have no change in rate, that means that this is going to be zeroth order. right? Anything that's changing in C does not result in a change in the rate of the reaction. Okay. So where else are, so what's the next one we're going to look at? What two experiments are we going to compare? Okay, so we're going to compare 2 and 3. So if we're looking at 2 and 3, what do we notice about 2 and 3? We have A is changing, right? We go times 2 as we go from experiment 3 to experiment 2. But we're also changing times 2 for our experiment in B. So any change that's happening, we can't tell what this change, let me change the color of this. Right, as we go from here, we're times 2, and if we go from here, it's times 2. So this change, right, is a little bit off because we don't know what that is happening or what is happening. Let me see. Right, this is times 8. So we don't know what is contributing to that change in rate. So 2 and 3 is not going to be our best option for comparing experiments because we have two reactants that are changing, right? We want to look for experiments that only one reactant is changing and the other one is being held constant. So if we're going to look at A, maybe a better combination would be 4 to 2. Because in 4 to 2, we see that we have B that's staying the same and we have C that's staying the same, right? So the only thing that's changing is the concentration of A. So as we go from 0.2 to 0.1, this is going to be times 2 in our concentration. And as we go from 0.01 to 0.005, I'm sorry, this is half. And this is times 1/2. If we're decreasing by a half, and then the rate is also decreasing by a half, what is that order for A? Good, this would be first order. Do you see why it's better to pick experiments 4 and 2 rather than 3 and 2? Okay, perfect. So what are the last two experiments that we're going to look at for looking at for getting our order for B? What equations or what experiments we're going to look at there? Yeah, 3 and 4 is our best option there. Because as we go from 0.1 to 2.4, this is times 2. And what's happening to our rate as we go from 0.01 to 0.04? Yep, so this is times 4. So if it's times 2 for concentration, but times 4 for rate, what's happening? What order is that? Good. This is going to be y equal 2. Great. Okay, so do we see why we had to pick the experiments that we did? If we go back to 2 and 3, right? We said that this one was not the greatest to look at because we had both A changing and we also have B changing. We said that our order for reaction A or for reactant A is first order and our order for reactant B is second order. So when A is doubling as we go from 2 to 3, we see that, right, that should double our reaction rate. And then we're also doubling B, but so that means we have to multiply it by 4. So our rate is getting multiplied by 2 and by 4, and that's where the times 8 comes from if we're looking at experiments 2 and 3. Yep, so the relationship's easier between 2 and 4 for reactant 1 because B in that case is not changing and C is not changing. We don't really care about C because it's 0th order anyways, but in both of those cases, the B and C reactants are not changing. So the only thing that is contributing to the change in rate of the reaction is the change in A's concentration. Yep. Okay, so then we still have to finish our problem, right? Just finding the orders is not the end of this problem here. So if we write our rate law, this is rate is equal to K, A to the first, B to the second, C to the 0. So when you have to solve for K, right, we don't know what K is yet. We can take any experiment and plug that in. So, right, you can pick experiment 1 and you're just going to plug in the rate. Anything that you plug in for C is going to become 1, so we don't need to include that anyways. And then you can solve for K here, right? You're going to multiply 0.120, square that, multiply that by 0.1, and then divide. So you should end up with B as your answer choice for K. That makes sense for question 13 here. Great. Any other questions? What quiz questions are we talking about? Yeah, I think I could talk about last week's quiz now. Is there a specific question from that? Um, Yep. So I'm looking at the quiz right now, just to find a good one. So yep, so we have this question where it was 2 NOCl, and that goes to 2 NO gas and Cl2 gas. So if we said that NOCl was decreasing at a rate of, I don't know, 3.45 times 10 to negative 3 molarity over seconds. What is the rate of appearance of Cl2? Okay, how would you solve this question? So we don't need to use a rate law for this question, actually. This one is just based off of your just rates of reaction. So, right, we know that for the change in concentration of NOCl over time, right, that's going to be the rate of disappearance. We need to have a 1/2 here, which means that the change in concentration of NO gas over time is equal to this, which is equal to which is equal to the change in concentration of Cl2 over time. And this portion here is your rate. So what we're looking at is taking the rate of this and making it equal to the rate of this. So if NOCl2 is decreasing at that certain rate, based off of our coefficients, should Cl2 be appearing or disappearing faster or slow? Should Cl2 be appearing faster or slower than NOCl is disappearing? Yep, so should Cl2 be appearing faster or slower than NOCl is disappearing? Based off of the coefficients. Yeah, it should be appearing slower. So because we have 2 in front of our NOCl and we have a 1 in front of our Cl2, for every 2 molecules of NOCl that gets used up, we only produce 1 Cl2 molecule. So the rate of appearance should be slower than the rate of our disappearance. So if we were to plug this in, when it tells you that the NOCl was decreasing at a rate of this, that's already telling you it's negative. So you can say that 1/2 of 3.45 times 10 to the negative 3 is equal to the change in Cl2 over the change in time. So if we just take 3.45, divide that by 2, then we know that the change or the rate of appearance for Cl2 is 1.73 times 10 to the negative 3 molarity over seconds, which is smaller than the rate of disappearance for NOCl. So that matches our prediction. And we know we need to use this because we're given a rate for the specific reactant or for the specific product. We're not given a K value. This is not K. This is not little k. This is just rate of disappearance or rate of appearance. It does not tell you the rate of the reaction. It's just telling you the change in concentration over time. So the change in the rate of change. It's not telling you reaction rate. It's just telling you concentration change. Um, Right, if you're just given a straight up rate like we're doing here, right, this is just a rate, that should tell you that you're just going to compare the rates of the products to reactants. If you see something with experiments, right, if we have experiment 1 and 1, 2, 3, this is going to tell you you want to use the rate law because you need to find the orders of the reaction first. And then if you have something where it tells you, right, K is equal to 3.45 times 10 to negative 3, 1/2 seconds, and it says it uses half-life, or you have two concentrations, right, that you know the change in concentration, or it tells you it's first order, right, or it tells you it's second order, then you probably want to use your integrated rate law. Because you're already given information about little k, the rate constant, and you know what the reaction order is. So you don't need to find that out by doing experiments. The experiments have already been done for you. So you can use the integrated rate law in order to determine, right, how long it's going to take to change that concentration. Or it's going to take, or you can figure out the rate constant based off of how long it took and what the order of the reaction is. Or you can find out what that final concentration is going to be because you know the rate constant, or you know the order of the reaction. So you can just plug that into one of your integrated rate laws. Yep, you want to use the Arrhenius equation when given two temperatures. Yep. Does that make sense for the difference in them? So like on your mock exam, right, question, oh, I remember it. Right, question 4 is asking, right, first order decomposition. This is telling you that, right, you already know the order, it's already decomposing by this, you're given a time component, integrated rate law. Yep. Yep. This one here, right, we're saying NH3 is consumed at a trial of rate 4.23. What is the rate of H2O being produced? Right, that one is telling you you have rate of a reactant, and you're asked about the rate of a product. This should just be straight up rate. And then we did the experiment 1, which shows you the experiment. Okay, so for question 9, right, we have reactions 1 and 2 have been determined to have the following equilibrium constants. They're given the 2, and we want to use equilibrium constant values above to determine the equilibrium constant value for the following reaction, reaction 3. So I want you to think of reaction 3 as your overall reaction that you're trying to get to. So we need to manipulate equations 1 and 2 in order to get to 3. So what do we need to do to 2 in order to make it match equation 3? Yep, so we need to, for C, we're going to take or for equation 2, we're going to flip it. What about equation 1? Yep, this one we need to multiply, we need to double. Okay, so for 1, we're going to double it, which is 4D going to 2B plus 2E. So what do we do to K1 there? Is it times 2? What do we do to K? So K is actually going to be to the power of 2. Maybe that's what you meant, right? But you're going to multiply it to the power of 2 because all of your coefficients now have an extra thing in front of them. So K1 will be equal to 8.41 times 10 to the negative 8. And then for equation 2, we're going to flip it. So that's 2b plus 2c going to a. And what do we have to do to K2? Yep, so it should be 1 over K2. So K2 is going to equal 1.75 times 10 to the 5th. And then if we add them up, right, we get 40 plus 2c going to 2e plus a. So what do we do to our k values? Yep, we multiply, so we're going to take K1 times K2. So it should be D, K3 is equal to 0.148. I think it's 0.0148. But you're going to take your manipulated Ks. To get that one. Okay, any questions? Yes, I did that right in order. I did this to that and this to that. So I just plugged in those. I plugged in I plugged in the manipulated versions. Yeah. Remind me what chapter 16 was. Is that kinetics? Yeah. Yep. So when we talk about kinetics, right, when you talk about kinetics, we need to know that higher temperature equals faster reaction. Okay, so, right, if we're looking at reaction coordinate like this is EA. And if we increase temp, then we're increasing the energy of that reactant. So our EA is now smaller. So, right, if we are increasing temperature, our rate of reaction is faster because we don't have as big of an energy gap that we need to get over. Okay, so higher temperature is faster reaction. Catalysts equal faster reaction. Because they provide alternate root. So we would have this guy here. This is no catalyst. And then with the catalyst, it might look like that. Sorry. Right, where we have a lower activation energy. So it's not changing the energy of your reactants or products. It's just providing an alternate route that the reactants can go through now that there is the catalyst present. In a reaction diagram, we have your reactants, you have your products. Stars are your activated complexes. And your plus signs are intermediates. Yep, so for little k as your rate constant, as temp increases, little k increases. So they have a direct relationship. For KEQ, this is exo or endothermic dependent. So if it is endo, that means that delta H is positive. And if it's exo, then delta H is negative. So if we have A plus B and delta H is negative, then that means we actually have A plus B plus delta H. So if we increase temperature, then we go towards reactants. But if we decrease temperature, then we go towards products. So it depends on if it's endo or exothermic, and then if you're increasing or decreasing temperature. The opposite is for exothermic. So if we have A plus B, but its delta H is negative or positive, excuse me, then that means we actually have delta H plus A goes to B. So this time, if we increase temperature, we go towards products. And if we decrease temperature, we go towards reactants. So it's not necessarily a direct or inverse for KEQ. It's very dependent on if it's endo or exothermic, and then if you're increasing or decreasing temperature. But for rate constants, anytime you have a higher temperature, you have a higher rate constant. Any questions on like the reaction diagrams we were talking about here? Anytime, right here to here, this is an EA1. Here to here, this is EA2. Here to here is EA3. So your largest EA is equal to your rate determining step, which is your slow step. And then the difference between reactants and products, this is your delta H. So this one would be exothermic because we have a lower product than reactant. But if we ended up higher, then it would be an endothermic reaction. Right, that's like the big like concept wise for chapter 16, I would say. And then the other concepts are the equations that we've been working with and the problems that we did on their mock exam. So like the comparing rates and then the rate law and then the integrated rate laws. Any other questions? Does that help a little bit with an overview of 16? Okay. So if you're asking if this right to your previous question, it's half right. Um, right, your if rate constant and temperature have a direct relationship, that is correct. If you increase temperature, you increase the rate constant because you're raising the energy of your reactants, decreasing the um, activation energy, so you're going to proceed with the faster rate. For equilibrium, that's not the case. They don't have a direct or inverse because it depends on the delta H of the reaction. It depends on if it's exo or endothermic. Anytime you increase temperature, whether it's endo or exo, you will have a faster rate, but that's because of little k. But big K is affected dependent on where delta H is for that reaction. So it's not a direct or inverse relationship. It's dependent on if it's endo or exothermic. And then you have to look at Le Chatelier's principle to determine if it's going to go left or right. Um, right, KEQ is equilibrium. This is just telling you after the reaction has proceeded in the forward and reverse reaction, do we have more products or do we have more reactants? Little k, this is your rate constant. So this is more products or reactants. And this is how fast a reaction happens. Okay, so they're different, right? Very different. As temp increases, little k increases here, right? Direct relationship. This equilibrium, you can't say if it's direct or inverse. If it's exothermic, then you have a negative delta H. That means that heat is released. So it's like it's a product, right? It's acting on the product side. So if you increase temperature, you're increasing delta H here, which means that we're going to shift towards our reactants in order to reestablish equilibrium. The reaction will be faster establishing equilibrium because we've increased temperature, and so therefore we've increased little k, but now we're going to have more reactants after the equilibrium is reestablished. But if we decrease temperature, we now have to produce more products in order to replenish the heat that was lost as we decrease the temperature. It's going to take a longer time for that reaction to reach equilibrium, but there will be more products at the end once equilibrium has been reestablished. Okay, so it's not an inverse or direct relationship because we're not talking about how fast something is going. It's talking about do we have more reactants or products at the end of the reaction when it comes to temperature and big K. Yep, yep. And then the same thing happens for an endothermic reaction. Right, that's a positive delta H. So that's saying that we have delta H plus A going to B. But this time, if we're increasing temperature, we're now producing more products. Right, opposite of an endothermic reaction. If we decrease temperature, we are increasing the reactants. Right, so different than an exothermic reaction. Okay, cool, great. Right, if you're increasing temperature, then equilibrium gets established faster than if you decrease your temperature, but it's just dependent on if you have more reactants or products at the end, once equilibrium is reestablished. 17 is equilibrium, yeah. So for 17, right, this is equilibrium. So this is big K, right? Big K is products over reactants. We only want can only have gases or aqueous solutions in our equilibrium constant. Your coefficients equal the exponent in KEQ. So if we have 2A plus B, sorry, if we have 2A goes to B, then KEQ here is B over A squared, right? The 2 in the coefficient becomes the exponent in KEQ. For KC, this is your concentration. So you need units in molarity usually. Usually, right? You just need some sort of concentration unit. And then KP, oops. KP is pressure. So you want ATM slash pressure units. Right, so KP is strictly for pressures, KC is for concentrations, right? So if you're given moles and also in the liter container that it's in, you need to switch to molarity first in order to figure out what KC is. You can convert between KC and KP using this equation, and delta N is equal to the moles of gas products minus the moles of gas reactants. And that's just from the coefficients as well. So if you have 2A plus B going to C, right, your delta N here is 1 minus 3 because you have a 1 as your coefficient for C and you have 2 and 1 for B. So you're combining those coefficients there. So here delta N is equal to -2. Okay. Any questions on that so far? And then I think the big thing is just, right, Q less than K, you're going towards products. Q equals K, you're at equilibrium. and then Q is greater than K, you go towards reactants. The delta N tells you the change in the moles of the gases. So that's only for when you're converting between Kc and Kp. This is they would ask you. They would say, is Kp equal to Kc? Or what is the value of Kp given the concentrations of gases here? It would be pretty obvious. They would put Kp and Kc in the same question. Like on your mock exam, not to sound like insensitive, right? But it would just put both of those in the question. And if you see both of those in the question, then use the equation. Like question 5, right? You have Kc is equal to Kp. So you need to compare Kc to Kp, and the way you do that is with the equation we just talked about. Does that make sense? Like why you would use it there? Okay, great. And we talked about question 5 last night in the review session. So if you go back and watch that video, right, I talked through like how to solve that. So you can watch it there too if you're still a little confused on it. I think we did that towards the beginning. But yeah, it would tell you like what is Kc given Kp or what is Kp given Kc. So don't you would I think you would know. I think you're aware enough to know you need to use it. Yeah. And then I think the last thing is really just ice tables. Um, right. Um, if you have 1 and 2 and 0, right? This would be minus x minus 2x plus 3x. So it's 1 minus x, 2 minus 2x, and 3. Yes, for Kp to Kc, the R is the 0.0821 because you're in like pressure units. So you want your pressure stuff. Yep. Yep, perfect. Okay, so just make sure you can do an ice table. I think there's been some practice on the mock exam too, if you're still confused. Yep, so sometimes you'll see a minus sign for the products, and that's just because, right, instead of having reactants starting off with, maybe you have the question. And for your ice table, right, you start off with 4 of this and 0 of these. So if you start off with no reactants, then you have to make reactants. So this has to be minus 3x. This is plus 2x. This is plus x. Yep, it's for the reverse reaction. Right, in this case, Q is greater than K, so you have to make reactants. Because Q technically is undefined or infinity. So that's much bigger than whatever the K value is. So you have to make a little bit of reactants. There could be. I mean, if it makes it easier for you, then you can flip the reaction to make it, right, if your products are the things that you have first stuff, you can flip the reaction and then you can just make it like they are the reactants, but then that means you have to flip the K too, that you're given. So It's just another ice table. It's just what is getting used up and what is being produced. Right, so if this has a K that's equal to 1, or we'll say 5. Right, if this K is equal to 5, the way that it's written, if you flip it, then you have 3C going to A plus 2B, right? It's the same reaction. It's just I'm now writing it as products to reactants is now reactants to products. So this K is now 1 over 5. So when you do all of your math, you just need to make sure you use the inverse K if you do it that way. But don't worry about it. It'll be okay. Yeah. Okay, well, it's 10:03, so I'll let y'all go back to studying or to class, whatever you're doing. If there's any other questions, I think we did almost the whole exam last night. Honestly, like my iPad's tired, sorry. We didn't do question 1. We didn't do question 7. And we didn't do question 14, but we did everything else. So if you have any other questions on the mock exam, it should be in last night's video. You do not have access to this document, but you have access to my videos. So pretty similar. I just can't give this away. It'll be distributed. Okay, cool. Yeah, of course, anytime. And then I'll have this recording posted probably by 2 o'clock today at the latest. I have to finish packing and get to lab. So if you have any questions in the meantime, just let me know, and then good luck tomorrow, and I hope you do well. And if you have any questions, feel free to email me too. Great, have a great rest of your day.